So this video is on rotational dynamics, or situations where we're interested in finding equilibrium or where equilibrium starts to break down. And so this is a continuation of torque and analyzing the forces. Torque equilibrium problems pretty much come in one of two flavors. Okay, there's seesaw problems where you need to balance the forces on two sides. Okay, the other one is kind of like, I describe it as rods with masses. They don't rotate, but you need to figure out what the various forces are. Okay, so these are two examples of seesaw problems. Okay, the left one is clearly a seesaw problem. It's a bar and there are masses on each side. Okay, the one on the right is actually a pulley problem, but we're looking for a situation where those two masses are going to be balanced. And it is still a seesaw problem in that I have a force being applied at a radius or a distance from the axis of rotation. Okay, so let's look at this first problem. Okay, this type of problem, we're usually trying to find x or a mass such that the system is going to be balanced. It gives you the center of rotation, or the fulcrum. Okay, and we need to remember that that fulcrum applies a force upwards as well. Okay, the mass of all the seesaw itself plus all the masses. Don't forget, if the seesaw board has a mass as well, that mass needs to be accounted for at the center of mass of the seesaw. But in this case, we just look at the torques. There are going to be torques that will try to make the object rotate clockwise or rotate counterclockwise. So if I look at this, okay, the forces times the radius, so m1g times d1 plus m3g times x minus m2g d2. Okay, the m2 is a minus because that would have been a clockwise rotation. Okay, if that force would have made the seesaw rotate in the clockwise direction. So that'll be a minus. Okay, you could also state this as clockwise torques equals counterclockwise torques. Okay. If there are angles involved, don't forget that you're going to need to apply a sine theta to these equations. This is another seesaw type of equation, okay? Here we're trying to find the masses such that the pulleys don't rotate, okay? It's important when we have these pulley problems to remember that it's the tension in the rope that makes the pulleys rotate, not the masses themselves. Okay, this is especially going to be true when the masses are accelerating, because remember, the tension in the rope is going to be the weight plus or minus the acceleration. Okay, so in this case, it's still going to be the same if there's no rotation, no acceleration. The weight of the masses is the same thing as the tension. And so here I have one that would, M1 would try to make the system rotate counterclockwise, positive, and M2 would try to make it rotate clockwise, positive. They're 90 degrees because where the rope touches, the rope is effectively always going to be tangential to your pulley. Okay, so meaning that that angle is 90 degrees and sine of 90 is just 1. Okay. The rods with masses, I think, are much more interesting problems, okay? And there are effectively two types of these problems as well, okay? There's kind of like the hanging sign or the extended crane bridge type of view on the left. And then there's the ladder ones, okay? These are interesting to me, at least, in the sense that there's no point of rotation being given in these cases. Yes, the one on the left, it looks like it's the hinge, but the ladder, there's no real point of rotation. Okay, and so you're in these situations where equilibrium exists, you can choose any point to be your point of rotation. It makes sense to choose the point where you can, because the radius is 0, you cancel out a lot of forces. So here's the picture on the left, okay? The spring scale and the bar and the mass hanging out there. In this case, my bar has a mass of 2 kilograms, and it's assumed to be uniform, okay? And so the point where gravity acts on that rod is at its center of mass, or its midpoint, Okay, so in this case, the free body diagram is shown here, and I need to look at both the linear equations and the rotational equations for forces. So for the linear equations, my up forces equals my down forces, and my left forces equals my right forces. Okay, so that's what those two equations are. Unfortunately, okay, I have three variables that I don't know. I don't know tension. Okay, there's a spring scale that I'm trying to figure out what that tension is. And then there's an X force and a Y force for that hinge. I don't know anything about those two forces. So I have three unknowns, but only two equations. And that's where the rotational part's going to come in. Okay, in this case, I declared my hinge because I know very little about those forces. Okay, it makes sense to declare that point to be the rotational point. So when I multiply them by 0, they effectively disappear from my equation. So in terms of the rotational forces, okay, the tension in that diagonal rope and that's where the sine 30 comes in, but it's tension times 0.6 times the sine of 30, or basically just the perpendicular component of T. Okay, then we have the two downward forces, okay, with the 4.9 and the 19.6 times their distances. They're already perpendicular, so I don't need to put the sine of 90 in, it's just 1. Okay, the Fx and the Fy do apply torques, but they apply torques at radius 0, so they disappear from my equation. So now I have three equations and three unknowns, and I can completely solve this using whatever methods I need to. Okay? The ladders are also interesting. So in this case, I have a ladder. There's no friction on the wall side, but there is friction on the bottom. Remember, that friction is static friction. It could be larger, it could be smaller than mu Fn, but it can't be greater. If the force needs to be greater, this ladder is going to start slipping. Okay, so the free body diagram is shown here. There's the force of the wall, which is the normal force for the wall. Two masses. Basically, there's one for the mass of the ladder, 98 newtons, and a person climbing up the ladder, 25 kilogram, a very light person, but still. Okay, and there's the force of the floor, and then there's friction. Okay, again, we have our linear equations. If this ladder is going to be in equilibrium, up equals down, right equals left. Okay, notice I purposely drew the force of friction in this case in the wrong direction. Okay, the reason I did that was twofold. One, if I drew it to the left, it kind of starts interfering with the down forces that I drew there. Okay, so it was kind of a space reason. But the conceptual reason is I don't want you to think it really doesn't matter that much which direction you are drawing these things. Okay. Because if they end up being negative, that's fine. It just means that you drew them the wrong direction. So if you did that, okay, you'll find that the force of the wall in this case is going to be a minus number. That's okay. It just means that I redefined my numbers in the positive and the negative direction. Okay, the force of the floor, most of the time with the forces, we're only interested in the magnitudes. Okay, not so much the directions. So the fact that I drew it in the wrong direction is not going to be a big deal. Okay, and then I have my third equation, which is the torque equation. In this case, I made the base of the ladder my point of rotation. I have two forces there. So by making that the point of rotation, multiplying them by 0, they disappear from my equation. And I can solve this because I can solve for the sine of theta and the cosine theta by dividing both sides and ending up with a tangent theta. So I have three unknowns in this case: angle theta, the force of the wall, and the force of the floor. And I can figure those all out using system of equation methods. Okay, so here's a couple of examples that I want you to try at home. Okay. I have a person on a diving board. All the things, pictures are shown there. There are two supports, 1 meter apart, shown in the picture, and you need to know what the forces on the diving board from each support happens to be. Okay, here's another one of those hanging sign problems. This one was actually almost more of a seesaw type of problem. this is a hanging sign type of problem, and I want you to try and solve that. Okay. The angle is shown there as 60, so always make sure you've got the correct angle. Okay, and here's another situation where Joey is climbing a tree trunk, and can he make it to the end of the log before the log starts to slip? Okay, so try those at home, and the answers will be given in the classroom. Okay, thank you.